The last time we were talking about the integral test, and I'll just remind you, essentially the integral and the series have the same behavior, right? If the integral of the function of the series converges, so does the series and vice versa. If the integral diverges, so does the series and vice versa. Um, the function you're working with is supposed to be positive, decreasing, and continuous. So, but usually that's something that's pretty true. Like the things we're looking at, it's usually not a problem. We then can, so I would also point out a couple things. Kind of like in 21B, like when we were learning about partial fractions, I would have said partial fractions is a method of later resort. You don't want to try partial fractions right off the bat. You want to try like a U sub first, or maybe integration by parts. Maybe not with the partial fraction, but like you never want to do partial fractions in the same sort of way. The integral test is not your go-to test for convergence or divergence. You typically are trying something else because usually integrating something is not that great. For example, if we were asked to like determine, I should write Co-21C, today is October 6th. If we wanted to find like, does the infinite series from n equals 1 to infinity of, I don't know, the natural log of n squared over n converge or diverge? We can show this diverges by the integral test, but we're going to learn other tests that are much more efficient to use. So the way we do this is, well, first of all, I probably should have started at n equals 2 because you start at n equals 1, it's technically 0. So, but fine, let's start at n equals 2 instead. My function f of x equal to the natural log of x squared over x is certainly continuous on the interval from 2 to infinity. It's definitely um, positive. And is it decreasing? Probably. How are we going to check? Do we have to check? Yeah, we probably have to check. Another reason why the integral test is not your go-to test, because you have to check these things first to even begin to think about using it. So we can check this. Okay, so my derivative is going to be the bottom times the derivative of the top, which is 2 natural log of x times 1 over x minus the top times the derivative of the bottom, all over the bottom squared. And if I simplify this, the x's cancel. I've got 2 natural log of x minus natural log of x squared over x squared. I can factor out the natural log of x, and I'm left with 2 minus natural log of x. And that's going to be negative as long as the 2 minus natural log of x part is negative, because the natural log of x part will always be positive. So yes, if 2 minus the natural log of x is negative, or in other words, if the natural log of x is bigger than 2, or in other words, if x is bigger than e squared. So is this decreasing? Yes, eventually, which is good enough. As long as it's eventually always decreasing, you can use the integral test. Again, more work than you're going to want to do. You can just put it on a desk if everyone's gotten it. But then you could certainly use the integral to say, cool, I'm going to look at the integral from 2 to infinity of the natural log of x squared over x dx, and then try to figure out if this thing converges or diverges. Kind of a pain. We got to do a U sub, have this improper integral, this. So if I was just doing the integral of the natural log of x, I should not try to squeeze this in here, even though I really want to. The integral of the natural log of x squared over 2 over x dx, if I do a U sub and let u equal natural log of x, my du is 1 over x times dx. I can rewrite this as the integral of u squared du, which is going to be u cubed over 3, which is then going to be the natural log of x cubed over 3. So then when I do this part here, I can say it's going to be the limit as b goes to infinity of the integral, right? God, this is so much work. This is definitely not the way to do this. And then you take the integral, which we already did. It's going to be the natural log of x cubed over 3. So it's going to be the limit as b goes to infinity of the natural log of x cubed over 3 from, I put 0 here, it should have been a 2, apologies, from 2 to b. We plug in our limits of integration, we get the limit as b goes to infinity of the natural log of b cubed over 3 minus the natural log of 2 cubed over 3. And since this part here is getting infinitely large, this is going to go to infinity, so it diverges. Way too much work to figure out that interval diverges. We'll see probably later today that there's at least one other good test you could have used here instead that's much, much, much faster. Okay, so one of the things the interval test does tell us, though, is it actually gives us the p-test. So the p-test says the following. The series from n equals 1 to infinity of 1 over n to the pth power converges if p is greater than 1, diverges otherwise. P can be negative, although it's weird to talk about P being negative here, because then you're just like, for example, the sum from n equals 1 to infinity of n squared. Technically, you could say that diverges by the p-test because your p is -2. But it makes more sense to say this diverges by the test for divergence because your sequence doesn't even go to 0. So this diverges by the nth term test or the test for divergence, right? The limit as n goes to infinity of your sequence n squared is definitely not 0, which means the series must diverge. So it doesn't usually make sense to talk about the p-test if your p is negative. On the other hand, something like, sorry, papers here. It makes a lot of sense to say the sum from n equals 1 to infinity of 1 over the square root of n diverges by the p-test. Because we can rewrite this as n equals 1 to infinity of 1 over n to the 1/2, and p equal to 1/2 is less than 1. Sorry, less than or equal to 1. And if your power p is less than or equal to 1, that series, that specific series of 1 over n to the p is divergent. It is less than or equal to. Because, and we've seen it, right? If n is equal to 1, or sorry, if p is equal to 1, apologies, we know that series diverges. The sum from n equals 1 to infinity of 1 over n to the first, we talked about how that diverged in class on Friday. And it diverges really by the integral test. So the p-test is just a specific application of the integral test. So you can show, most of your teachers probably already did it. I don't think it's worth spending our time doing it, but we can show that the integral from 1 to infinity of 1 over x to the p dx converges if p is greater than 1. And we can show, and I'll point out, I'm going to write this next part as 2 parts. We can show that this integral from 1 to infinity of 1 over x to the p dx diverges. I'm going to write less than 1, even though I know I said less than or equal to 1, if p is less than 1. And we already know the integral from 1 to infinity of 1 over x to the first diverges. Right? We definitely know that. We showed it last time. It's natural log of x plugging in infinity, you get divergence. Here's what I would encourage you to keep in mind for these two separate cases, essentially. The reason that this is converging is because when you integrate 1 over x to the p and your p is larger than, in fact, let's just go, I'll try not to do all of it, but here's kind of the thought process. If p is greater than 1, when you integrate 1 over x to the p, I'm not going to worry about the limits of integration here. You're really integrating x to the negative p And when you integrate x to the negative p, what do? Add 1 to the power, divide by the new power. Now here's the point. Since your power was bigger than 1, like 1.2 or 2 or 7, well, when it becomes a negative power and then you add 1 to it, it's still going to be negative, right? Your power was more negative than -1. So when you add 1 to it, it's still negative, which means essentially it's still in the denominator. So the whole idea here is if p is greater than -1, then you're going to integrate this and your x to the negative p plus 1. I don't really care about this here, but this negative p plus 1 is still negative. Or rewriting it, you can rewrite it as 1 over negative p plus 1 times x to the positive p minus 1. And since p was larger than 1, p minus 1 is bigger than 0. But then check this out. You essentially have 1 over x to a positive number. And then if you plug in infinity for x, that's when you get super duper small. So that's why if p is larger than 1, when you integrate, you essentially still have x to a power in your denominator. And that's going to go to 0 if x is really, really large. Conversely, if p is smaller than 1, I would imagine thinking of like 1/3. When you integrate 1 over x to the p, you still get the same garbage. You get x to the negative p plus 1 over negative p plus 1. But now, since p was something like 1/3, negative 1/3 plus 1 is positive. So this negative p plus 1 is a positive power, which means then if you let x go to infinity or plug in b, let b go to infinity, you're going to get infinity. So this is going to diverge. This goes to 0. This goes to some sort of infinity. That's why that works the way it does. So that's the p-test. If you have, and I should be very specific here. If you have 1 over n to a power, that series diverges if p is less than or equal to 1, converges if p is larger than 1. But the thing is, like, you can play with it then. For example, what about this series? The sum from n equals 1 to infinity of 5 over n squared. Well, I could pull out the 5 and say that's equal to 5 times the sum from n equals 1 to infinity of 1 over n squared. And then this definitely converges. So 5 times it is also convergent by the p-test. The reason I'm pointing to this is people get a little nitpicky. For example, on the other hand, the sum from n equals 1 to infinity of 1 over like n squared plus 1, even though it looks super close to being a p-series, it's not. It's not 1 over n to a power. Exactly. So you cannot say this converges by the p-test, even though we'd like to be able to say that. It's not true because you're not using the p-test. If you wanted to do it the hard way, you could integrate it. You don't want to integrate it. I mean, you could. Actually, it's not true, right? The integral of 1 over x squared plus 1 is the arctangent of x. Ooh, you know what? This one is worth mentioning the integral test for. I know I said you didn't want to integrate it, but I lied, or I was wrong, is probably the right thing to say here. If you do the integral test, I'm not going to test all the things. I know that 1 over x squared plus 1 is decreasing. It's certainly decreasing, right? If x gets bigger, that definitely gets smaller. It's definitely continuous, and it's definitely the other thing that I forgot what it was. Positive for sure. So this is something people like to throw at you because it's funky. What's the integral of 1 over x squared plus 1? Right. So we have the limit as b goes to infinity of the arctangent of x from 1 to b, which is equal to the limit as b goes to infinity of the arctangent of b minus the arctangent of 1. Arctangent, I can spell. Okay. As b goes to infinity, what's the arctangent of b? Drum roll, please. It is pi over 2. We'll show you why in a second. What's the arctangent of 1? What's the angle that if you take tangent of it, you get 1? Pi over 4, 45 degrees. So this integral definitely converges to pi over 4, which means this series also converges. Now, is this the best way to do it? No. Even though it's kind of neat, it's still not the best way to do it. But the one thing I didn't remind you of is this limit is pi over 2. So let me show you what I mean. So if you graph the arctangent, just as a quick reminder, here's good old tangent with vertical asymptotes at negative pi over 2 and pi over 2. Looks like this, kind of, And there's more of it to the sides. And then if you take the inverse function, you reflect the graph across the line, y equals x. Every x thing becomes a y thing, every y thing becomes an x thing. So every vertical asymptote becomes a horizontal asymptote. And y equal to the arctangent of x looks like this. It's got horizontal asymptotes at pi over 2 and negative pi over 2. And it has this shape. So we can see that, oh yeah, as the x values get really, 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 really big, the arctangent values get closer and closer to pi over 2. Or said differently, if you take tangent of values that get closer to pi over 2, your outputs get really, really large. But we're looking at the other thing. That's why that limit is what it is. And that's kind of the best way to see it. But I feel like I'm kind of dancing around the next thing. So let's go ahead and get to the next thing, which is the comparison test. And two of the examples we did are really much better candidates for the comparison test. So, sorry. So we should maybe come back to that in a minute, though. So here, the example we just did, the sum from n equals 1 to infinity of 1 over n squared plus 1, instead of doing the relatively not too terrible integral, we can say the following. Well, check this out. We can see that 1 over n squared plus 1 is less than 1 over n squared for all n that's greater than or equal to 1. It's actually true for all n, but we only care for the n's that you have to deal with in your series. So we're starting at 1. Bless you. But that means whatever this series adds up to has to be less than whatever this series adds up to, the sum from n equals 1 to infinity of 1 over n squared. But we know that this series converges. And this series also has to converge because it's adding up to something less. Now, here I'm kind of leaving off some explanation. Here's the real explanation that your teachers probably have said, but I'll say it also. So here's the idea, really. So I'll say this first. So your series must converge. But here's a better explanation of what's happening. Let's look at the sequence of partial sums for a moment. So for my series, from n equals 1 to infinity of 1 over n squared plus 1, we know that our sequence of partial sums, so like our S1 is 1 over 1 squared plus 1, our S2 is 1 over 1 plus 1, plus 1 over 4 plus 1, and so on. Okay, and so on. So our nth partial sum is 1 over 1 squared plus 1, plus 1 over 2 squared plus 1, plus all the way to 1 over n squared plus 1. Two things. Thing one, our series from n equals 1 to infinity is bounded. How do you know it's bounded? Because it's less than another series that converges. It's bounded. It's bounded above by this series that's bigger than it, and below by 0, or pick some negative number, but definitely, or even 1/2. So definitely it's bounded. You know what else it is? It's monotonic. Look at this. Well, I should apologize. I maybe misspoken a little bit here. I should have been talking about the sequence of partial sums being bounded, not the series itself. So what I should really say here is my sequence of partial sums. So my sequence of partial sums Sn is certainly bounded, and it is also monotonic. Which is true for almost any sequence of partial sums where the terms are positive. Because if you keep adding on a positive term, your thing is always going to get bigger. It's increasing every time, right? Your sequence of partial sums, as long as your sequence itself is positive terms, the sequence of partial sums always is going to be monotonically increasing. So this sequence of partial sums is bounded by whatever this thing adds up to. It's monotonic, and by the bounded monotonic convergence theorem, it has to converge. So that's really what we're exploiting when we use this direct comparison test, is that since this sequence for this series is less than another sequence that's convergent, whose series is convergent, we get to say that our series is also convergent because the sequence of partial sums is bounded and monotonic. So the limit as n goes to infinity of Sn must exist by the monotonic bounded convergence theorem. I'm sure there's a better name for that. Or in other words, if your sequence is less than a sequence whose series is convergent, then your series is also convergent. Likewise, or in a similar way, we can show that another one of our series that we started off with is divergent. So let's look at the sum from n equals 2 to infinity of the natural log of n squared over n. We used the integral test for this one before, and it was kind of a pain. But here's what we can say now. We can say that the natural log of n squared over n is definitely bigger than 1 over n. Okay, as long as n is bigger than or equal to 3. So if you really want to be kind of a pain about it, you could break this up and say it's the sum from n equals 3 to infinity of the natural log of n squared over n. And then you're tacking on the first term that you cut off, which is the natural log of 2 squared over 2. And then we can say, oops, and then we can say that this part's going to diverge. And then if you add something to a divergent thing, it's still divergent. So here's the idea. My sequence, natural log of n squared over n, is definitely bigger than 1 over n. And we know that the series from n equals 3 to infinity of 1 over n is divergent. It's a p-series. Technically, I started a little later, but if you add up something to infinity and you cut off the first two terms, does it still add up to infinity? Let me phrase. If something adds up to infinity and you cut off the first two terms, which are finite, does the rest still add up to infinity? You bet it does. It definitely has to. So this is divergent, and then so this sum from n equals 3 to infinity of the natural log of n squared over 2 is also divergent. So we can conclude that the sum from n equals 2 to infinity of the natural log of n squared over n is divergent. So long story short, if your sequence is bigger than the sequence that's divergent, the series, let me write the words instead of just trying to say all the words. So this is the direct comparison test. So there's two parts to it. Part one, if your AN is less than or equal to your CN and the sum of CN converges, then so does the sum of AN. On the other hand, if AN is bigger than or equal to CN and the sum of, oh, I think I used a BN here, probably. Let's use a BN instead. And the sum of BN diverges, then so does AN. The sum of AN, I should say. So if you're bigger than something divergent, you're divergent. If you're smaller than something convergent, you're convergent. All that being said, with the assumption that everything is positive. So I probably should throw in a if AN is greater than or equal to 0 here, if BN is greater than or equal to 0 there. Because if you say you're less than something that's convergent, but you're like a bunch of negative numbers that get very negatively large, you're going to add something divergent. So usually this test comes up mostly for things that look like rational functions or kind of combinations of rational functions. What do I mean by that? Let's look at some examples. So how about, for example, the sum from n equals 1 to infinity of the square root of n divided by n squared plus 2n plus 4. Here's the thought process. I wish I could make it never look straight here. One second. I feel like it's very crooked. Okay. So here's the thought process. If it's a rational-ish looking function thing, powers of n over powers of n, you want to look at the highest power of n divided by the highest power of n. So in this case, we're comparing this to the sum of n to the 1/2 over n squared, which is equal to the sum of 1 over n to the 3/2. So let me ask you, is this thing that I want to compare it to a convergent series or a divergent series? Convergent, the P series, with P being larger than 1. So since we're thinking we want to compare it to something that converges, that means we've already decided we think it converges. So the not great thing about the direct comparison test and the limit comparison test is you have to kind of decide before you do the problem. Do I think this thing is convergent or divergent? Cool, I think it's convergent. I'm going to compare it to something I know converges. Or I think it's divergent. I'm going to compare it to something that I know diverges. But you have to start off deciding this to me looks like something that does blank. I'm going to compare it to something that does the same thing. The issue with the direct comparison test is the thing once you've decided convergence, it has to be true that the thing you have is less than the thing that you're comparing it to. In this example, we are fortunate it is, right? It's definitely true that the square root of n over n squared plus 2n plus 4, well, that's definitely less than the square root of n over n squared. Because if you make your denominator smaller, you have made your fraction larger. So this totally works. That's less than that. So we can say that we can conclude that the sum from n equals 1 to infinity of the square root of n over n squared plus 2n plus 4 converges. Usually, when you write something converges or diverges, you also write the test you have used. So we say converges by direct comparison. It gets trickier. For example, if I had something like the sum from n equals 5 to infinity of n squared over n cubed minus n plus 5. And now I'm thinking I want to compare it to n squared over n cubed, or 1 over n. So we're thinking we're going to compare it to the sum from, or the sum of 1 over n. I don't really care about the from right now, which we know is divergent. So now we need this thing to be bigger than 1 over n. So is it the case that n squared over n cubed minus n plus 5 is bigger than 1 over n? Well, not immediately, because we didn't just make the denominator smaller. We made it smaller and bigger. So, yeesh. Let's see here. You could cross multiply, say n cubed bigger than n cubed minus n plus 5. Well, the n cubes cancel. So, yes, this inequality is true as long as n is greater than or equal to 5. So we can say that, yeah, oh, look, we started at 5. We're in good shape here. We might have started on purpose. So, yes, certainly n squared over n cubed minus n plus 5 is bigger than or equal to 1 over n as long as n is bigger than or equal to 5. Which kind of makes sense if you think about it, right? Because if n is 5, the negative 5 plus 5 cancels, and you've got n squared over n cubed, which is 1 over n. So here we can say that this series diverges by direct comparison. Let's get one more example. Let's say we have the sum from n equals 1 to infinity of 1 over n times 4 to the n. Yeah, question.
Can I ask a clarification?
Totally, yes.
Like this, the direct comparison test.
Right.
That,
So one more time, the last part.
like the direct comparison test, that's like a branch of the comparison.
Well, I would say so it is the comparison test, but we often specify the direct comparison test in contrast to the limit comparison test, which is coming up next. So that's why I'm emphasizing the director, because we are explicitly saying this thing is less than this thing, or this thing is bigger than this thing. Whereas with the limit comparison test, you don't have to be so direct about things being exactly less than the other thing all the time. And we'll get there in just a moment. So here we can say that this is, well, It's certainly true that 1 over n times 4 to the n is less than 1 over n. But that doesn't help me, because the series for 1 over n is divergent. And being smaller than something that's divergent tells you nothing, right? If I'm smaller than infinity, I could also be infinity, or I could be finite. So being smaller than a divergent series is useless, or it doesn't tell us anything helpful. On the other hand, we could also have said our sequence 1 over n times 4 to the n is less than 1 over 4 to the n. And the series for that, the sum from n equals 1 to infinity of 1 over 4 to the n, is the same as the sum from n equals 1 to infinity of 1/4 to the nth power. And that is a convergent geometric series. So this is convergent. Since our sequence is less than the sequence of the convergent thing, our series is also convergent. So this series is convergent by direct comparison. It is useful. I only said one more, but I'm actually gonna throw one more at you. So one more example of direct comparison here. Something like the sum from n equals 3 to infinity of the natural log of n over n squared. Typically, you could say that the natural log of n is going to be less than kind of n to any power you want eventually. Some typical choices are like the square root of n or the cube root of n or just n itself. So it's certainly true that the natural log of n is less than the square root of n. Think about the graphs of them. The graph of the square root of n starts off a little higher and it remains higher. you might have some, like if you did a really small root, like if you did like the 100th root event, it would, the natural log function would be larger than it for a while, but then eventually the 100th root would overtake the natural log function. Or said another way, logarithmic functions are the slowest functions we've got. They grow slower than any power of x, even x to the 1/1 billionth power. It takes a while, but eventually x to the 1/1 billionth is going to overcome. Just like eventually e to the x is going to overpower x to the 1,000th power. X to the 1,000th power starts off a lot bigger and it's bigger for a while, but eventually that exponential function is going to overpower it. Exponentials always overpower powers. Fractional powers always overpower logs. No qualifications to be said. So here we can say that the natural log of n is less than root n, and then the natural log of n divided by n squared is less than root n divided by n squared, which is just 1 over n to the 3/2. We know that this series converges, so this series converges by direct comparison. That said, direct comparison often doesn't work or is really, really a pain in the butt to make work. Let's look at some examples of that. Something like the sum from n equals 2 to infinity, to infinity of n over n cubed minus 1. Certainly to my eyes, I'm thinking, cool, this looks like n over n cubed, which is 1 over n squared. So I am thinking this is similar to the sum from n equals 2 to infinity of 1 over n squared. And we know that this series does what? Converges, because our p is bigger than 1. The problem is this thing here isn't less than 1 over n squared. N over n cubed minus 1 is actually bigger than n over n cubed, which is equal to 1 over n squared. Right, my denominator got bigger, my fraction got smaller. I just have to think about it for a second. I'm like, oh yeah, like if n was 3, 3 over 27 minus 1 is bigger than 3 over 27, right? Smaller denominator, larger fraction. That's a problem because to use the direct comparison test, if we're trying to show convergence, our sequence of the thing we're trying to show convergence has to be smaller than the sequence of the thing we know is convergent. Not. There's a few ways around this. One way is to do some algebra, and like you could say like multiply this by 2 or something and then show it. It's a pain in the butt. If it's not easy to find a strict inequality, you want to then move towards the limit comparison test. So the limit comparison test, most of the time, in my opinion, is a superior test. There are occasionally times where the limit comparison test won't work and the direct comparison test will, but they're relatively few and far between. So here is the idea. To determine if some series is convergent or divergent, let the sum of Bn be some other series whose behavior is known. So again, you have to decide. In this example up here, I'm going to choose this series that I know converges. And once I've made that choice, the only thing that can happen is either I can show that the original series converges or my test is inconclusive. I cannot compare something to a convergent series and conclude that it diverges. I cannot compare something to a divergent series and conclude the original converges. So again, with the comparison limit comparison test, before you start doing the test, you have to decide if you think your thing converges or diverges and compare it to something that has that behavior. Here's what we're going to do then. So we find the limit as n goes to infinity of the unknown sequence divided by the known sequence. And it's equal to some value L. This this test is often phrased in different ways. Some people phrase it the following way: as long as L isn't 0 or infinity, both series do the same thing. So if your limit is finite and not 0, both series will diverge or both series will converge if you're comparing it to a converged graph. But that leaves off some corner cases. So the way we typically phrase it is the following way. If the series you're comparing it to is convergent, then your unknown series is also convergent as long as your limit is not infinity. Meaning it's okay for your limit to be 0 or some finite non-zero number. Here's the thought process. If this limit is 0, that means the top thing is smaller than the bottom thing. And if the bottom thing series converges, then the top thing series, where you're adding a bunch of things that are smaller, also converges. On the other hand, if the thing you're comparing it to is divergent, then your original series is also divergent as long as your limit is not equal to 0. But infinity is okay. Because if your limit of this is infinity, you're essentially saying the top thing is way, way bigger than the bottom thing. And if your bottom thing series diverges and your top thing is bigger than it, then your top thing series also diverges. Here's the idea. We are thinking really that AN is sum L times BN. Now, that's not really always true, but it's essentially true. If you go out far enough, AN divided by BN being really, really close to L for infinite number of terms means that your ANs are just L times BN for infinity. And then whatever BN does, multiply that by L, AN does the same thing. So as long as L is something weird like 0 or infinity, you're like, well, okay, all these terms add up to 1,000, and then you multiply that by 5, all the other ones add up to 5,000. They both converge. Or all these add up to infinity, you multiply that by 5, this one adds up to 5 times infinity, which is infinity. The reason we're talking about these corner cases here is just to be consistent about the whole thing. So big picture. We find something to compare it to, we take this limit, and then we say stuff. So let's look at this example again. So we're going to limit compare this series n equals 2 to infinity of n over n cubed minus 1 to this series, which we know is convergent. So then the limit as n goes to infinity of the unknown sequence, I should say the sequence whose series' behavior is unknown, but it's easier to say the unknown sequence, divided by the known sequence. And we get the limit as n goes to infinity of n over n cubed minus 1 times n squared over 1, which is the limit as n goes to infinity of n cubed over n cubed minus 1, which is 1. Which means essentially, if you go out far enough, the terms are the same, right? The AN is 1 times the BN, or they're very, very close to each other. So then we can say, since this series converges, the sum from n equals 2 to infinity of 1 over n squared, so does our series by limit comparison. So that's the basic idea, is you look at your series, you try to find something to compare it to, and then you take the limit of the unknown over the known, and you hopefully get a nice finite non-zero number, because you have to think about whether it's 0 or infinity. Let's look at, we got 5 minutes left. Let's examine something like, let's look at this one. Let's look at the sum from n equals 1 to infinity of sine of 1 over n squared. What should I have been doing every time that I didn't do any of these times? The divergence test. But all these examples are ones where the sequence has a limited zero. But I should have been mentioning that, right? So here as well, if I take the limit of this, 1 over n squared goes to 0, sine of 0 is 0. So the test for divergence wouldn't help us, but it's still good to think about it. So now, what am I going to compare this to? This one's a little tricky. We're going to limit compare to this series. Actually, the same one we just used. This one is like, I feel like this test is a good, this is it. It's not a good test question. It's a good test question if your teacher likes to be tricky. Because it's really easy if you know how to do it. If you take the limit as n goes to infinity of sine of 1 over n squared over 1 over n squared, there's two ways to deal with this. One way is to use L'Hopital's rule. I don't love that. The other way is to remember a thing from 21A, which says if you've got sine of a thing over the same exact thing and that thing is going to 0, sine of 0 over the same 0 goes to 1. And you would be perfectly valid by just saying 1 here and not really showing any other work unless your teacher says otherwise. But they shouldn't, because this is like a thing people do all the time. Or you can use L'Hopital's rule, but it's kind of a pain in the butt. But that means that the bottom and the top thing have to have the same behavior. So that means this series from n equals 1 to infinity of sine of 1 over n squared, since this series is convergent, this series also converges by limit comparison test. Here's the place I think this is kind of most useful when you have terrible rational expressions. For example, the series from n equals 1 to infinity of 2n squared plus 5n plus 1 over 7n to the fifth plus 2n cubed plus 3. That looks terrible. Here's what we're going to do. We're going to limit compare this to the sum from n equals 1 to infinity of highest power in the top over highest power in the bottom. Or in other words, the sum from n equals 1 to infinity of 1 over n cubed, which we know is convergent. So then we write out the limit as n goes to infinity of 2n squared plus 5n plus 1 divided by 7n to the fifth plus 2n cubed plus 3. We maybe skip the step of dividing by the other thing and just multiply by the reciprocal. Right? This is your limit as n goes to infinity of your an divided by bn. There's your an. There's your bn. There's an divided by bn or multiplied by the reciprocal of bn. What's always going to, yeah. Sure. No, it's not that n has to approach 0. It's that the thing you're taking sine of has to approach 0. So 1 over n squared is going to 0. So you could say, another way you could deal with this if you like, is you could say, let's let x equal 1 over n squared. Then I can rewrite this limit as the limit of sine of x over x. And if n goes to infinity, where does x go to? Right, so it's the limit as x goes to 0. Oh, look, we're getting exactly the same sort of deal. Or if you want to, it's totally legit to use L'Hopital's rule here. Your derivative at the top would be cosine of 1 over n squared times negative 2 over n cubed. The bottom's derivative would also be negative 2 over n cubed. The negative 2 over n cubes cancel. You get cosine of 0, which is 1. Here, this works out very nicely. You get the limit as n goes to infinity of 2n to the fifth plus other terms we don't care about over 7n to the fifth plus other terms we don't care about. And the limit is going to be 2 over 7, which means both series have to have the same behavior. So our series, which I don't want to write again, converges. All right, that's all the time we have for today.